Yeah, the YouTube was convenient.
Yeah, much more than Zoom apparently is. That's what I have like 3 emails from my Chem 2 students saying, yeah, could you do that more? I mean, I had one that pointed out today that you can't, on Zoom, you can search for words because the transcript is searchable, and then you can go to that moment in time. I don't think you can do that with YouTube.
No.
But it was preferred.
Yeah, with this, I'm just planning to go start to finish.
Yes. Well, that's exactly right. And even if you do need to skip forward, it's easy enough to tell where we're at because of how I'm doing this. All right, but number 44, yeah, we are going to make these two with our given ingredients. All right. Well, that's not going to shell it down too much. I should just be to do HNO3 and H2SO4 to put a sulfur on there, because it is just going to go to that 2 position preferably. And that's still not deactivated enough. That's just 2 carbons. Shouldn't need to worry about that rearranging, so Friedel-Crafts should work there just fine. And it's also going to be perfectly fine putting it in the alpha position. Oh, you know what? I know what they wanted. They want us to point out that we can use a different, and we should use a different Lewis acid. And on thionyl, I want to say it is 10 chloride. I'm going to back up just a couple pages to the summary reactions to guarantee that's right. Oh, it's not even in the summary reactions. It's in the book here though. Just got to go up to where we do our 5-member rings and Friedel-Crafts on it. Well, I thought it was in this book. There we go. This is what I was looking for. Yeah, so there's with the sulfur in there instead of like a nitrogen, and it will do Friedel-Crafts, but we can use 10 chloride rather than aluminum chloride. Just a little bit less acidic of a Lewis acid, but essentially does the exact same thing. Oops. And since they're both going in that 2 position, that should be easy enough to do. That one, we shouldn't have too much difficulty at all. All right, next one's a little bit trickier because that particular ring is deactivated because of the nitrogen, and our 2 first spots that go on there are kind of like the meta, so 3 position. So I'm going to put a nitro group on there first. And that will definitely put it in the 2 position, or the 3 position. Then we're going to activate it, or not activate it, protonate that. All right, now my gut kind of tells me that now being an activator, I should be able to just do bromine and iron bromide. And I am going to get this because that's para to the ammonia, but I'm also going to get probably a little bit too much of the bromine right there as well, ortho to that, and might even get the other ortho. So we are going to get mixtures.
Would PBR work?
No. No, because if I try to do it, so if I have it as an OH and then turn it to PBR, the only way to get the OH on there would be using the diazonium salts, and I can't do that on this deactivated ring.
Okay.
This is our best bet. We're going to get mixtures, but majority of it will be the para on that opposite side. Still not a great yield, but it's our best one.
You know, sometimes the book is very theoretical.
And they omit where they end up making mixtures. Okay, I think we're ready to actually look at chapter 28, but I do want to mention what I'm probably doing on the test. This looks like I can do this way. So, where chapter 19, the difficulty on the test is going to be that it's a huge amount of review. So it by itself is covering more things than just chapter 18, 19. I might do this next test just on that. And I'll probably decide that this weekend.
All right. Is that going to change when worksheet 28 is due?
Yeah.
Okay.
Yeah. I might be moving 28 till the next test, and then we can include everything. If I leave it on here, we're just going to do the electrocyclic, the very first one, and the cycloadditions. And we already have done the cycloadditions, technically speaking, because those are Diels-Alder. But let's just make this decision now, make this easy. What do we have left according to the syllabus? I think I have
It's 2 more chapters.
20 and 21. Okay. Bring up the calendar here. All right, so moving 28 to the next test is not going to be that big of a deal. And it is only moving it 1 week. No. Our final is that Monday, isn't it?
Final is what, May 6th?
I need to put this here. And then I can go to the next. You know, I do think that makes a little bit more sense to just go ahead and move it there. and leave both those chapters in there, because chapter 20 is the harder of the two, being the carbohydrates. 21 is not nearly as bad, but both of those are kind of short chapters. But that will save us some hassle on getting ready for this coming week. And what we can do the rest of the day, rather than start looking at chapter 28, we can instead just look at worksheet type problems.
Okay. Yeah, worksheet 28 is long.
Yeah, but you'll see it's,
Repetitive.
well, how do I want to put this? So if we look at chapter 28, they start out with your molecular orbital diagrams,
Mm-hmm.
making it seem darn important. And it was in the original understanding.
Right.
But the biggest thing you need to pick up on is this nice little thing where they're in phase on the outside, they're out of phase, they're in phase, they're out of phase, they alternate.
Right.
And it reduces every bit of this stuff, regardless of how complicated and how the questions are. It reduces everything to nice little, where's one of our tables. And all your reactions can be determined based on just calculating the pi bonds,
Oh,
even and odds.
Okay.
So we can reduce the heck out of this, and actually that really helps it. And when I plan my recording for the chapter, I build it off these tables. I kind of want to do all of it, because I had it figured I would drop the electrocyclic, but I think I'm just going to do them all. Not the I drop the sigmatropic, but I think I'll just do them all and just move this to the next test. Yeah, I think that makes the most sense. All right, so let me make an announcement real quick.
It works for me. 19 is enough to worry about.
Test 4 will only cover, I'm going to leave it very big, too. Oop, wrong keyboard. $19.
Yeah.
Yeah.
19. Does that mean that test 5 and the final is now the same thing?
Yeah.
Okay. So the last test we take is not cumulative, it's just the last 3 chapters?
Yes.
Okay.
Isn't that how I had it set up before?
That's how we wound up
Yeah.
doing it.
Yeah, I just have the-
semester,
Yeah.
But it started out on the syllabus as cumulative.
Yes. But this, I always do Chem 2, where this last one is independent and not cumulative. Because technically speaking, it is. Because there's no way you're going to do any of this stuff without building off previous stuff. So it's cumulative in its nature just because of that. All right, so I made that announcement. Let's bring up some worksheet problems. Actually, I don't want to do it that way.
Probably want to tell people about the typo.
Yeah, I think that's a good one to start with. You know, I actually started to make a video of it, and about 2 minutes, because I didn't really actually get your methylene comment. I mean, I understood what you meant, but I didn't actually. I'm looking over here on these guys. But I'm going to start right there on this little recording, and I'm going to make a updated post on this. But technically, that there should be a 3. And I have no idea why it got to be a 2.
Yeah, look at that. And, okay, how do I do Hoffman with this?
Yeah, because it's it is just a straight Hoffman, but that doesn't mean it's trivial. And especially when we throw in something like that, I actually don't even know if you could do Hoffman and make a triple bond out of it.
Mm-hmm.
Okay, so do we want to just try to do these in order? I mean, I know Joanne and I actually looked at some of these yesterday. Do you have any questions in particular you want to look at? Picking up where we were yesterday?
Actually, haven't worked since yesterday.
Oh, yeah, well, I can understand that. And it was late in the day. So why don't we just start at the top so I can point out little tricks that are going to possibly throw us out.
Oh yeah, the stereochemistry.
Did you have one in particular?
I wanted to make sure that I got the flip number 4 right.
Oh, and how it actually, when it actually opens?
Yeah.
Well, it's very symmetric, but it's actually under acidic conditions. So under acidic conditions, we do technically protonate that first and make this ring positive. And so this is able to do a backside attack.
Right, does that, in that case, does it count as an SN2 and then it reverses? Reverses position?
Well, the side it ends up going to, and which side is that in this case?
It's going to be the one that left side, because the right side is 2 methyl group. I think.
Well, what's our nucleophile here? Or better yet, when we do this, which side does the nucleophile go to? More substituted side or less substituted side under acidic conditions?
Is it the less substituted?
It is the nucleophile will end up on the more substituted side. So since this is our nucleophile, it's going to end up over here, and we're breaking this bond. Now, how the stereochemistry will go, those two get to be opposite sides. So I was going to originally draw this almost looking the exact same. That's supposed to be on the O, but I couldn't put it on there because I drew it poorly. I am going to put it up there. And then we'd have a base come in there and deprotonate that. But you notice how, think about our original drawing, these guys were flat on the paper. So when I finally redraw it, that first carbon, I'm going to have this coming up at us. and the H going behind H. And on the paper going down is the OH. And then going up out of the paper is going to be the OCH3 once it gets deprotonated. CH3 is still up, and the other CH3 is down. But I technically don't even need to show that on that second location because it loses its stereochemistry anyway, since there's both methyls.
Okay.
Yeah, I like that. All right, and our drawings up here, just to do them quick. Piperidine, it's like cyclohexane with a nitrogen. Oxetane, cyclobutane with an oxygen. Cyclopentane, an epoxide in 1 and 2, and 3 is an ethyl. Why did I bother to say cis? Oh, I'm saying this.
Right. It's 2 wedges.
Be hard to do that without wedges. No, that has to be wedges. This is what's the wedge. So this is up as well. So let me redraw that bigger over here. So regardless of how we draw it, the epoxide would have to go the same direction because it is just a triangle. So I couldn't do up and down and come to the same location.
Right.
So the cis means that the ethyl is also up. Hmm. Okay.
Well, the other thing that comes immediately to mind is where exactly do you put the N that you've got IUPAC naming, you've got a substituent on the backbone, and you also have to talk about the connection with the nitrogen.
Are we talking about just an amine or a nitrogen in a ring?
Amine.
Okay.
I think it's a question coming out.
Let's just. Is it a nomenclature one?
That one.
This
Okay.
one. Good. Good, good, good. We'll do that. All right, so naming it as an amine, we're going to just choose whichever side is the longest and make that our backbone. Now, if this had continued on, our backbone keeps on going on. So the amine doesn't have to be at the one location per se. But that's going to be a substituent and this. And our backbone is hexanamine. So we have a methyl and an ethyl. No, that's propyl.
Yeah.
5-methyl in propyl. 1 hexanamine.
Okay, that's why I wasn't clear on whether or not the N counts in the alphabetical order.
The weird thing is, there are 2 ways that are kind of acceptable here. You will see times where the N, anything attached to the N will be listed in front.
In parentheses.
Not necessarily in parentheses.
I think that's what Marvin
It put it in parentheses. I wonder why I did that. I'm gonna put that in Marvin. I want to see what. I'm gonna put this in Marvin. Actually, what I'm gonna do, because Marvin is such a cool little program. See if it draws roughly the same thing. Almost perfectly. But now if I tell it to name it, 5-methylhexyl propyl. Oh my gosh, it's naming the amine. That's a common name technique. It's naming the two substituents calling off the nitrogen as separate things. I gotta admit, I don't think I've ever seen that done that way. So I have no idea why. But that's definitely not IUPAC. I don't even think that's old IUPAC.
Right.
Now, old IUPAC would have the N-propyl in front just because the propyls got listed. Everything else would be the same.
Right.
But even old way, if I change this ever so slightly, that would keep our hexamine the same, but these are both methyls. New way would have N5-dimethyl.
Oh. Okay.
Old way would have N-methyl 5-methyl.
All right.
Of course, right?
Sure.
Yeah. But for the most part now, current literature, we're going to see the N listed just like it is here and still alphabetizing by this.
Okay.
But I'm kind of
So-
surprised by that name, to be honest.
So N works like the prefix works.
Mm-hmm.
Cool.
Mm-hmm. All
I
right.
couldn't get a straight answer from the IUPAC's website.
No. And I would be very surprised if you ever got off that website and thought, wow, that was beneficial. Not saying it's not, it's just more of, we're getting into gray areas on some of the nomenclature where there's more than one possible name that's acceptable. Quite a few times. All right, so, wait, what are you doing? Oh, it's trying to change my background. So, what is the stereochemistry of the product and the acid hydrolysis of trans-2,3-butane? So, butane, trans. Oh, I know what they mean. And we're going to say the epoxide's coming up at us. Acid hydrolysis, we're just going to have OHs on opposite sides, right? So I'm going to leave the carbons flat on the paper. One OH would be up in that case. The other one would be into the paper. They'd have to be opposite. Oh, and that's cool, because think about this. If I rotate this end so that carbon is flat on the paper, this OH would be up. So if I do a rotation, just to the one side, just to the right side, just so that carbon's down, this thing was wedged into the paper, it would be wedged out of the paper. And so we have a mesostructure. Dioxane. That's a lame name. Draw the structure of the residue. So CH2, CH2, N, N, and there's technically two H's if it's, well, that'd be the positive ion. Must be, because it's asking why is pKa lower.
Easy resonance.
Well, if I compare this to I have bond angles approaching 109. So any base that comes in here is going to have a little bit of hindrance here. Yet over here, when that base does that, it's going to get to that a little bit, or a heck of a lot easier, because that's 106. That's a 60-degree bond angle. So this hydrogen is more out in the open. Less hindered. By adjacent bonding groups. Yeah, I like that. And you were saying resonance?
I can break those bonds to be double.
Yeah, but I have to rip off an hydrogen off one of those carbons too. Wait, do I have... I want a small one. 3-membered with a nitrogen. Okay, yeah, all right. I just wanted to make sure. So if it had been the AZI RNIE, we do have a double bond in there. But this one is just 3-membered ring with a nitrogen. So I'm not going to have to, I'm not going to see resonance play into it because I don't have another double bond in there yet. Yeah. All right. Well, piperidine is relative basicities. Well, piperidine. Lone pair here. I think that's two nitrogens that are... No, that's a nitrogen and an oxygen, isn't it? Are they opposite one another? I think it's a 6-member ring with an oxygen and a nitrogen. Yeah, oxygen and a nitrogen. And they are opposite. technically, that is still outside. Well, that's a withdrawing group, definitely. Going to withdraw the electrons into that ring, which would pull these back. So this should be less basic. Roll. Adyne 2-methyl. That one's easy. Lone pair is delocalized or is in a p orbital. Delocalized into the ring. Nitrogen doesn't own all those electrons. Yeah, that one's easy. Need to have that on the test, don't we? Ah, I just actually splashed my nose with water. Drinking problems. All right. Now we're on to definite review, right?
Is that an airplane reference?
Drinking problem?
Mm-hmm.
I love that movie. And technically, since we're in the means chapter, we also need to point out that this also makes NH3 positive Cl minus. What a lame question this one is. That's just a diazonium salt. Now watch out. Had I had a nitrogen on there anywhere, it would have ended up making an alcohol out of the diazonium, which would have turned into a carbonyl. Oh, seeing this, I'm like, that's not what 13 does. But no, 13 is just a secondary amine with a carbonyl.
Oh, what's that called? Amine?
It's an enamine.
Enamine.
Because the nitrogen attaches, that nitrogen has 3 bonds. We ripped off an adjacent hydrogen from the carbonyl. Made an enamine. Ah, 15. Hofmann elimination. Okay, so it doesn't matter which way of these I go, so I'm going to break that bond on my first Hofmann, and I will be left with a double, single, 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 N, CH3, CH3. And then my CH3I. This is all going to stay the same. This is one I did with last night, and I made it look horrible because of how I chose to do it. All right, but then we're doing Hoffman again. We're going to break this one off, and we will get double, single, 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 double, and a N with 3 different CH3s off of it. And on this one, that's our only product. 16, we end up with 3 potential products. Because the easy one to break off, that side there, the reason I say it's easy is because it only gives us 1 product. We'll make a double bond there and everything else stays the same. If we break over on the right side, we can put the double bond out, or upwards. Hoffman product, the major product, is always the one with the most hydrogens. But both these two, the two on the far left, both have 3 hydrogens off the double bond. The reason is this one is our major product is because not only does it have the most hydrogens, it was also the easiest the easiest carbon-nitrogen bond to break because it was just a primary carbon attached to the nitrogen. So make that a better one to break, and it gave us 3 hydrogens, so that's our major product. Ooh, another one. So my first step replaces that hydrogen and the lone pair with a methyl. And Hoffman is going to break here or here. I was thinking we were going to get 3 products, but we're only going to get 2. Alright, so I'm going to look at breaking the left one first. These as a lone pair. And that means the double bond could go here or here because I have both locations. And I can actually do that. So I could have a double bond there. Or here. Looking at the other bond breaking though, I'll do that in blue. This would still be connected to the nitrogen. And we go there, there, and this would be our double bond. Two hydrogens off the double bond here, 1 off the double bond here. This one has 3. This is their major. Alright, the next one's a cope elimination. Gives very similar products to Hoffman, except that the nitrogen is going to be ended up attached to an OH. Makes a hydroxylamine. The other OH of the hydrogen peroxide is going to rip an H off one of these adjacent positions. So we're going to have a double bond start with here because we're breaking this off. And one of the carbons it's attached to, if it has a hydrogen, that's a potential hydrogen. So we might rip off this one, we might rip off one of those. But that's a hydrogen, so I can't do anything there. So one of my products, and I'll go to the left, CH2 double bonded to now a CH, and then everything off of that still looks exactly the same. The other possibility is to go right along here and make my double bond. I'll do that in green. And if I do that, I'll put this wedged one up and this wedged one up. And that should be our product there. Same rule on major product as, well, Hoffman and Cope have the same rule. So major product is the one with the most hydrogens, so this one is the major. I'm actually getting kind of a headache from looking at this computer screen. What have you guys done to me? Not as bad as this week at home. It's more that I went ahead and scheduled an eye doctor appointment. Good idea. Alright, so the N stays the same, but we end up attaching it to an OH. And starting from here, we can have a double bond that goes inside the ring or out to that methyl. Inside the ring, or turn the methyl into a methylene, which would be our major product because it's got 2 hydrogens off the double bond. Alright, after step 1, I want to draw that different. I'm going to rotate it, put this nitrogen right there. After step 1, I'm going to replace that hydrogen with the methyl and add another methyl. That thing's still going to be the same. Then we're doing Hoffman. So we're breaking that bond or that bond. If I break that green one, it becomes a lone pair. The rest of this is still the same, except there's going to be a double bond right there. Red one, two hydrogens, 3 hydrogens, major. Cope elimination. I can't do anything with that benzene ring, so I'm going to leave that attached, and methyl doesn't have any of the carbons off of it. So one of my products with the nitrogen just has an OH on there. This guy, we're going to form a double bond between these two and rip off that H. So we have a CH2 double bonded to a CH. CH2, CH3. That question's worded kind of odd. That implies there's more than one product. have not. That's it.
Well, I think what you mean is show.
Products.
Oh, show the products.
Yeah. This is one of the first chapters where that's really gotten to be a lot more important because they're always organic molecules. Because I do get a kick. We introduced Hoffman back with our alkenes, but if you had left off the amine that was being produced, that wasn't necessarily considered wrong. Because we were actually always asking about the alkene that's being produced. Alright, well, first step here is going to put a triple bond nitrogen on there. And then I'll put hydrogens across it. That one's easy enough. So, chromic acid turns a primary alcohol into a carboxylic acid. Ethynyl chloride turns a acid chloride into an acetyl chloride, or carboxylic acid into acetyl chloride. Acetyl chlorides with ammonias get turned into amines. And then lithium aluminum hydride and water turns amides into amines.
Yeah, that's off the, yeah.
Chromic acid. So cool. NH3. And this is the only one that's always 2. You don't do just one of those. Step 1, nitrogen, nitrogen, nitrogen. Step 2, NH2, and technically N2.
Do I have to show the nitrogen gas?
Huh? No, because it's not organic.
Okay.
Okay. 25, that's that intermediate that's made in the Cope elimination after you've added the... No, this is the intermediate in the Hoffman reaction.
Yeah, heating quaternary nitrogen
Yeah.
in basic conditions.
Now we're just going to heat this thing up. No, this is OH. That's Cope. This is Cope. All right, so I know the nitrogen's going to stay with that CH3 and that CH3, and technically this one's going to stay intact too, because even though that's a CH2 and bonded to something, that carbon doesn't have any hydrogens. So one of my products is just an amine. So, okay, this is Hoffman. So the only bond I can really break off on this one is this guy. But that does give me 2 possible alkenes. I can have CH2 double bonded to that CH to the CH2, CH3. Or I could have CH3 to the CH double bonded to a CH, CH3. This would be the major. because there's more hydrogens off of it. Oh, look at this. Because this end is the same two alkenes are formed. But this is cope. So that nitrogen gets an OH attached to it. Same major product. This one's a rehash of something you've seen before. I've missed a carbon. 1, 2, 3, 4, yeah. Doing it like this because I want to show why this is stabilized. Got 3 little resonance structures of that 5-member ring with the deuterium and the hydrogen added that location. But we kind of need to just show that that DSO4 minus comes in and takes a hydrogen with it. Two R's. Better base. I don't own my electrons. That's a little bit too... That's not very scientific, is it?
I'm just renting.
Yes. I have to share my electrons with these other 2 carbons that have to share electrons. That's the adopted sibling that still shares toys. This is the typical redheaded stepchild that no one really loves. He gets to keep his toys. Wait, that's opposite, isn't it? This one's easy, but this finishes up the paper. So it's a great stopping point. Goes in the 2 position.
Goes on 2 position?
Mm-hmm.
Huh. I thought it would be meta-directed.
Well, the interesting thing, if it's a 6-member ring with a nitrogen, you see the 3 position is more popular.
Uh-huh.
If it's a 5-membered ring and nitrogen, oxygen, sulfur, any of the heteroatoms, 2 position is preferred.
Okay.
But it's such an activated ring that if both two positions are filled, it will go to the third position.
Got it.
And that's harder to do with a 6-member ring with nitrogen because that ring is actually deactivated, which is hilarious. Activated ring. Deactivated. Just to make it confusing, right? But there is a reason that I always draw it with those lone pairs inside and these outside. Activating, deactivating.
Ah, nice trick.
Also drastically changes their basic properties. Pyrrole, the 5-member ring, is not basic at all because it doesn't own those electrons. But pyridine, it's less basic than a typical nitrogen, but it is actually closer to the pKa's in the 30s and so. All right, I think we're at an awesome stopping point, mainly because we're out of time and I gotta let my head rest for some reason. You people are driving me crazy apparently.